Okay, half-life. So some radioactive substances, what happens is they disappear over time. They get smaller. So we wanted to talk about what the half-life means. It's the time that it takes for half of whatever you started with to decay away. Or another way to look at it is it's the time it takes for whatever you started with to only have half of its original mass remaining. So let's work a problem with this polonium-210. Everyone's favorite isotope of polonium has a half-life of 140 days. So it takes 140 days for whatever you start with to only have half that amount of mass. Half of it's gone, but half of it remains. Okay, so suppose a sample of the substance has a mass of 300 milligrams. Let's see if we can find a function that models the amount of the sample remaining at time t. So some keywords as we go through this, the half-life, that's pointing us towards the continuously compounded interest formula, or the law of decay is another way to point it out. All of these with that keyword half-life are also going to use that A equals P times E raised to the RT formula. Okay, the half-life though is 140 days. We always want to start with the half-life information. Please always start with this information in your initial setup. Okay, we want to suppose we have a sample of the substance has a mass of 300 milligrams. So 300 milligrams, another key value here. The 210 from polonium-210 is not giving us a number to plug in. Okay, so let's see if we can fill into our formula. So to find this function that models it, we want to start with the half-life. So we begin with the half-life is 140 days. So that's a time frame. Let's go ahead and plug that in for t. The other thing we know is the substance has a mass of 300 milligrams when we start. So we can say 300 milligrams is our starting amount. That's going to be P. But here's the kind of missing information if you don't know what half-life means. Remember, half-life, whatever you start with, this 300 milligrams, after this amount of time goes by, the 140 days, which is the half-life, you're only going to have half of whatever you started with remaining. So if we started with 300 milligrams, we're going to end up 140 days later with half of that, so 150 milligrams. So whenever you set up the half-life information, these have to have the same correspondence, that whatever you start with is double whatever you end up with. Now we don't know what our rate is, so let's do some solving down for R. So in filling all of this in, we can go ahead and say, well, 150 equals 300 e raised to the r times 140. And then to solve this down, you're going to get used to these. We have r's up in the exponent. That makes this an exponential equation. We want to isolate this e to the power, that exponential part. So let's get rid of the 300. So as we divide both sides by 300, this works out pretty nicely on the left-hand side just to be 1/2. Then we have e raised to the r times 140 remaining on the right-hand side. At this point, we have e to a power. Let's utilize a natural log on both sides. So if we substitute both sides into a natural log, that's a 1/2. We get a natural log of 1/2 equals the natural log of e to that power. But what's going to happen is natural log and e to a power, logarithmic and exponential functions are inverses of one another, so we're going to get some pretty nice canceling out over there on the right-hand side. So we can say natural log of 1/2 is going to be equal to r times 140. We're only going to be left with the exponent. And to finish this up and get r on one side all by itself, we need to get rid of the 140. And by get rid of it, I mean we'll divide it both sides by 140, thus isolating r all by itself. So this is an exact rate that we found here. Remember, if you're going to estimate this, put this into your calculator, you need to keep a lot of decimal places. I think most of our homework, though, likes exact answers more than anything else. So let's go ahead and keep this as an exact answer. We'll say our rate is the natural log of 1/2 over 140. All right, so as we're trying to find this function that models this situation for us with our polonium-210, we've got our rate. Our starting amount is still going to be 300, but we've already utilized this half-life information, so the 140 and the 150, So we don't need to plug that in over here as we're trying to get our model. For our model, we won't know our A and we won't know our T. So we can say A of T, right? We're creating a function where you plug in different values of T is going to equal 300 e raised to, and I know this looks strange, but the natural log of 1/2 over 140 multiplied by T. And all of this is up in the exponent of the e. If you like, you can put a big set of parentheses around that entire exponent. Sometimes students find that helpful. All right, so part B. Let's find the mass remaining after 1 year. Okay, so the mass remaining after 1 year, I know we all want to plug in 1 for our time frame, but remember our time frame up above was 140 days for the half-life. So if we want to plug in 1 year, we have to use that converted over to days. So 1 year is equivalent to 365 days. You want to stay consistent on your units. So when time was given in days initially, we want to keep it in days as we plug in throughout the rest. So let's just plug into our formula we just created. So we can say T of 365 equals 300 e raised to the natural log of 1/2 divided by 140 multiplied by 365. And again, a big set of parentheses around that entire exponent sometimes is helpful as far as getting to the right answer without making any mistakes along the way. So I got this, as I put it all into my calculator, to be 49.237. And I guess maybe I should point out with my units, that was 300 milligrams initially. So this would be milligrams, what remains. All right, one last follow-up question here on part C. We want to know how long will it take for the sample to decay to a mass of 200 milligrams. So a lot of the information is the same here. We want to start with the same amount, right? We had 300 to begin with, 300 milligrams. Our rate is going to be the rate that we just solved for in part A. So I have to utilize natural log of 1/2 divided by 140. We want to know how long, so we don't know our time frame. And then the sample to decay to a mass of 200 milligrams. So we end up with 200 milligrams. That's going to be our accumulated amount A. All right, so let's plug it all in and see what we can solve for. So we'd say 200 equals 300 e raised to the natural log of 1/2 over 140 times t. And again, all of this, the rate and the time, up in the exponent on e. So solving this down, let's isolate the e to the power. So I'm thinking let's get rid of the 300 first. And by get rid of it, I'm just moving it to the other side by dividing. So we can say 2/3 equals e raised to the natural log of 1/2 divided by 140. And I get it. These are some additional steps to keep copying down this fraction, but that's okay. All right, next up, we have e to a power. Let's counteract that by utilizing a natural log. So if I put a natural log on both sides, we get natural log of 2/3, and then natural log of e to that power. But what's going to happen is on the right-hand side, we're going to get some nice canceling out going on because natural log and e to a power, these are inverses of one another. So the inverse function property says you get some nice canceling out. You're just going to be left with that exponent. So bringing the exponent out, getting rid of the natural log and the e from the right-hand side. Now the rest of the solving down shouldn't be too bad. I realize we have a fraction multiplied by t. I'm going to take this as 2 separate steps and multiply by the fraction first, or multiply by the 140 to eliminate this fraction on the right-hand side. So now we have 140 natural log of 2/3 equals the natural log of 1/2 times t. All right, to get t all by itself, we still need to get rid of this natural log of 1/2. So let's go ahead and divide both sides by natural log of 1/2, and we'll have it. So that'll put t on one side all by itself. And sure enough, this is an exact answer going on over here. But if we're trying to answer this question, like how long until we only have 200 milligrams remaining, that kind of question, we're probably would rather have like an approximation, right? If you tell someone, oh, yeah, in 140 multiplied by natural log of 2/3, all divided by the natural log of 1/2 days later, we're going to have 200 milligrams remaining. They'll probably look at you like you're a little bit strange. Instead, let's get a decimal approximation. For this one, I got 81.89, and that'll be consistent with our units from before. So just like we had 140 days for our units up here and 365 days for the mass in 1 year, we're staying consistent with these units that our time frame is still going to be in days. So almost 82 days later, we're going to only have 200 milligrams remaining. Okay, so I hope this helps out as we're setting these up, answering multiple questions on exponential modeling. Good luck to you on it.